Signals from the Void: The Mystery of Fast Radio Bursts. A NEXION documentary. Imagine a radio flash so powerful it briefly outshines entire galaxies and then vanishes, leaving only a single clue: a burst of radio energy that lasts as little as a few milliseconds. These are fast radio bursts, cosmic whispers from the deep universe that arrive like impossible postcards. They arrive without warning, with no obvious origin, and with a message we are only beginning to decode. Tonight, NEXION follows the hunt. From backyard radio arrays to world-class observatories, from careful lab tests to wild speculation about intelligent signals. This is Signals from the Void. Chapter 1: The First Knock. It began with a surprise. In 2007, astronomers analyzing archival data from the Parkes Radio Telescope in Australia discovered a single, intense burst of radio waves recorded in 2001. It lasted barely 5 milliseconds, but in that instant, it released as much energy as the sun emits in days. At first, some feared the signal was terrestrial interference, a faulty instrument or a passing satellite, but further analysis suggested a true cosmic origin. The discovery was odd, and then more odd as more of these flashes appeared. Each burst seemed to come from a different patch of sky. No repeating pattern was immediately obvious. No associated visible explosion. The phenomenon was rapid and rare, and the universe, it seemed, had learned a new way to speak in radio. Chapter 2: What We Know. Characteristics of FRBs. Fast radio bursts, or FRBs, have a handful of defining features. They are bright in radio wavelengths, incredibly brief, typically milliseconds, and often appear to come from cosmological distances. The dispersion of their signal, the way lower frequency radio waves arrive slightly after higher frequency waves, reveals how much interstellar material they pass through, and from that dispersion, measure astronomers infer enormous distances. Some FRBs have been observed only once. Others, like the famous FRB 121,102, were observed to repeat, sometimes dozens or hundreds of times. Repeating FRBs open new avenues. If a source repeats, astronomers can point telescopes and search for a host galaxy, a local environment, or a counterpart in other wavelengths like X-ray or optical. Those repeated detections have allowed teams to pinpoint host galaxies, confirming that at least some FRBs originate in distant galaxies billions of light years away. Chapter 3: The Tools of the Hunt. Detecting FRBs is part detective work, part global coordination. Radio telescopes from single-dish giants like Arecibo, before its collapse in Parkes, to interferometers like the Very Large Array and the Canadian CHIME telescope, monitor the sky for telltale spikes. CHIME, designed to map hydrogen across the universe, unexpectedly became an FRB machine, discovering dozens of new bursts thanks to its wide field of view. Once a burst is detected, rapid follow-up matters. Optical telescopes, X-ray satellites, and even neutrino observatories mobilized to see if the radio flash left any multi-wavelength trace. Teams analyzed the polarization of radio waves, their frequency structure, and their timing. Every detail can hint at the physical conditions near the source. Magnetic fields, the density of surrounding plasma, or the dynamics of a compact object. Chapter 4: Leading Natural Explanations. Scientists have proffered many natural models. The leading contenders include Magnetars. These are neutron stars with super strong magnetic fields. When a magnetar cracks or reconfigures its field, it can release enormous energy suddenly. Observations in our own galaxy in 2020 found a radio burst associated with a magnetar flare. Strengthening this model, magnetars explain intense energy and rapid timescales, and they can exist in dense environments that contribute to the observed dispersion. Merging compact objects, collisions of neutron stars or neutron star black hole pairs release massive energy, but these events tend to be one-off and are rare. They could explain singular FRBs if the timing and energetics align. Extragalactic flare stars or exotic plasma processes. Some models invoke plasma lenses, shock interactions, or relativistic jets interacting with surrounding material. These scenarios can create complex frequency structures and explain some observed millisecond features. Each model has explanatory power, but none yet explains every observed property, especially the variety among FRBs, from one-off flashes to prolific repeaters. Chapter 5. The Repeater Puzzle. Repeaters are the wildcard. If a source repeats, and especially if it repeats with complex temporal behavior, we can begin to study its environment. FIB 121,000, 102, one of the first known repeaters, lives in a dwarf galaxy with strong star formation and persistent radio emission, suggesting an energetic nebula nearby that could indicate a young magnetar inside a supernova remnant or a persistent engine like a low-luminosity active galactic nucleus. Another repeater, FRB 180,916, exhibited a 16-day activity cycle, several days of bursts, followed by quieter periods. A periodicity suggests an orbital driver, perhaps a magnetar orbiting a companion or precession of a jet. Periodic behavior opens the door to predictive observations and deeper study, yet even periodic repeaters present puzzles. Sometimes their bursts are ordered and complex. Sometimes they are chaotic. Chapter 6. The SETI question. Are any FRBs artificial? Whenever an unexplained cosmic signal arises, the question of intelligence appears. The search for extraterrestrial intelligence, SETI, community asks, could FRBs be technological? There are reasons to be skeptical. FRBs occur too far from us to be practical broadcast beacons for interstellar communication. Their energy requirements are extreme, but other proposals suggest FRB-like signals could be leakage from powerful astrophysical engineering, for instance, beamed energy from advanced civilizations powering star-moving or propulsion systems. Most astronomers favor natural explanations because they are consistent with known physics and because a technological origin would require extraordinary evidence. Yet, FRBs are a vibrant reminder of why science must remain both skeptical and open. The universe sometimes surprises us, and we must be prepared to test all hypotheses against data. Chapter 7. Rare clues. Polarization, frequency structure, and local environments. FRBs carry fine-scale information. The polarization of radio waves reveals magnetic fields along the path. Some FRBs show extreme Faraday rotation, indicative of an intense magnetic environment near the source, such as a magnetar embedded in a dense nebula or near a massive black hole. The frequency structure, the pattern of peaks and notches across frequency, can indicate lensing by intervening plasma or interference from compact emission regions. These diagnostic features allow astronomers to reconstruct local conditions. For example, bursts with extreme rotation measures likely emerge from environments rich in magnetized plasma, perhaps young supernova remnants, galactic centers, or compact objects in dense star-forming regions. By combining host galaxy imaging with these signatures, researchers can piece together a source's life story. Chapter 8. A Cosmic Census. What FRBs tell us about the universe. Beyond the mystery of origin, FRBs are valuable probes. Their dispersion measures provide a way to quantify the density of ionized gas along vast cosmic distances, effectively helping map the distribution of baryons, the ordinary matter that is otherwise difficult to find in the intergalactic medium. FRBs can thus help solve the missing baryon problem, where much of the universe's normal matter resides. Moreover, FRBs can test cosmology, because they are bright and detectable at large distances. They can become precise tools for measuring the expansion of the universe, for probing intervening galaxy halos, and even for detecting gravitational lensing if a burst is split into multiple images by intervening mass. Chapter 9. The Race to Localize. Localization, nailing down the exact position of an FRB, is the gateway to understanding. Radio interferometers and rapid response arrays now localize bursts to host galaxies with subarxicon precision. Instruments like the Australian SKA Pathfinder, the Very Large Array CHIME, and the European VLBI network coordinate to catch bursts in real time. Localization has transformed FRBs from curiosities into astrophysical tools. With each localized burst, we learn more. Star formation rates, metallicity, and whether the source sits in a galaxy's outskirts or heart. These details inform models and narrow down plausible progenitors. Chapter 10. The Human Story. Observatories, backyard arrays, and global collaboration. The hunt for FRBs is not confined to ivory towers. Hobbyists and university groups contribute, and open data policies accelerate discovery. Citizen scientists mine archives for missed bursts. Global collaboration, shared data, rapid alerts, and multi-wavelength coordination has been essential. This is a story of tools and tenacity. Engineers building real-time pipelines, programmers optimizing GPUs to search terabytes of data, and astronomers ready to swing optical telescopes within minutes of an alert. It is also a story of patience. Sometimes the sky is silent for weeks, and sometimes 100 bursts arrive in a single month. Chapter 11. Wild Ideas and Responsible Science. Speculation has its place. The media sometimes gravitates to extraordinary explanations, but scientific progress relies on testability and the scientific community welcomes novel models, but each must be evaluated against observations. When a new theory appears, researchers design observations to falsify it. That is how science advances, by iterative confrontation between idea and cosmic reality. At the same time, FRBs remind us that discovery is often incremental. Today's surprising burst may be tomorrow's cataloged phenomenon. Responsible science combines curiosity with methodological rigor. Chapter 12. The Future. New telescopes and new windows. The future of FRB science is bright. The square-kilometer array sky will revolutionize sensitivity and survey speed. Next-generation radio. Arrays with greater bandwidth and lower noise will catch fainter bursts and measure their structure with exquisite detail. Paired with optical, X-ray, and gamma-ray observatories, they could reveal multi-messenger counterparts, if they exist. Machine learning accelerates discovery, sifting real transients from terrestrial interference and instrumental noise. The increasing automation of radio astronomy expands the sky coverage and reduces reaction time. In the coming decade, FRB rates will grow from hundreds to thousands, and their statistical power will soar. Chapter 13. What if we find a pattern? Imagine a day when a repeating FRB can be imaged with enough detail to resolve its local environment, or when a set of bursts reveals a pulsation or encoded structure that points unambiguously to engineered signals. The scientific implications would be staggering, but even without intelligence in the equation, a pattern such as periodicity, polarization cycles, or consistent multi-wavelength counterparts will illuminate new physics. From plasma processes in extreme fields to novel compact object behavior, every signal we collect is a data point in a larger story. Interpreting that story requires humility and creativity. Chapter 14. The Call to Wonder. The universe sends us small, ephemeral postcards. Fast radio bursts, brief and brilliant, remind us that there are phenomena we have yet to understand. The hunt for FRBs blends high technology with fundamental curiosity. It is a reminder that our cosmos is active, surprising, and sometimes inscrutable. If you felt that itch, that pull toward the unknown, subscribe to NEXION. We follow questions that change how we see reality, and we bring rigorous storytelling to the greatest mysteries our planet and universe present. Which scenario captivates you most? An exotic astrophysical engine like a Magnetar, a cataclysmic one-off collision, or the remote possibility of engineered signals? Tell us in the comments below. The most insightful replies may be featured in our next episode. This was Signals from the Void, the mystery of fast radio bursts, a NEXION documentary. Thank you for joining the search.